All right, so let's go ahead and get started on organic chemistry. And the first thing we have to talk about is bonding and whatnot in organic chemistry. But before we get started with that, let's talk a little bit about the origin of organic chemistry. So organic chemistry is very old, definitely. Synthetically, maybe a little bit different, but generally it's a very old subject. And organic chemicals were thought to be some things that occurred only in nature, and it came only from something that was living, whether it was plants or animals. That's where it thought that organic chemicals came from. You couldn't think about getting organic chemicals from inorganic chemicals. Okay, inorganic is anything that is not living, right? And organic was considered to be anything that was living. And so when Wheeler first synthesized an organic compound, urea, from something that was inorganic, then suddenly everything changed. Okay, and so it's not changed as in like you didn't change the whole thing about organic chemistry. Now it was just a different outlook on organic chemistry, that, oh, you can actually make organic molecules from inorganic material and from other things. You don't really just have to obtain it from nature. Okay, that's the kind of mindset that was changed, okay, which tells you that the more you learn about things, the better you get and the more it opens doors for you. So once this started, then it changed the whole perspective, and then organic chemistry started as a whole new field, as in, more synthesis, more research, more knowledge, okay, about how we can synthesize molecules, how we can make them better, etc. So now how do we classify organic chemistry? How do we look at organic now? Organic chemistry now we define as anything that has carbon compounds, and those carbon compounds are bonded with hydrogen, oxygen, sulfur, nitrogen, phosphorus, and halogens, which, if you think about it, is really all the right-hand side of the periodic table, all the non-metals, okay? So which includes really all the halogens, group 7, group number 6, which is oxygen, sulfur. Remember, as you go down a group, then elements become more metallic in nature, all right? So that's why all of these things are actually on the top of the periodic table and on the right-hand side, except for halogens, which are really almost all truly non-metals, okay? So this is now the definition, okay, for organic chemistry, that is study of carbon compounds. One thing I want to just kind of mention to you as a review for organic chemistry or for the periodic table is that carbon is really the only non-metal in group number 4. Okay, and so the other elements, they start becoming metalloids and then metals as you go down the group. Group number 4 is like the most interesting group of entire periodic table. That's how I consider it. But of course, other people like other elements as well. But for me, group number 4 is very interesting because it has all sorts of elements in it. And carbon, of course, is the main element there, which comprises, makes up all the organic molecules. Is really interesting. Carbon also is very interesting because it can have both kind of bonding, okay, which means it can have ionic bonding and covalent bonding as well. So all of these elements that I just mentioned up here, which is, all the non-metals, hydrogen, oxygen, sulfur, etc., those are going to be the covalent bonding, okay? But that's not all that we're going to learn in organic chemistry. We will learn about some of the metallic bonding also with carbon, all right? So those will lead to other kind of chemistry, also very interesting chemistry. Then there are some compounds of carbons that are not considered to be organic, even though they have carbon and they have oxygens or hydrogens, but they're not considered to be organic. And those examples are given here, like carbon monoxide, carbon dioxide, carbonates, and so on. Okay, so some of these polyatomic ions and some small molecules that we have learned before, those are not part of organic, although methane is. Okay, methane is something that you do learn in Gen Chem, which is CH4. That is part of organic, but some of these other ones are not. Okay, so not everything that has carbon is going to be organic. Like coal is not organic. Of course, you obtain it from nature, but coal or petroleum products, these are, some, not petroleum, I shouldn't say petroleum, but coal, diamond, these are not organic. These are just carbon elements. Okay, so you have to be a little bit careful about what you consider to be organic, even if it has carbon in it. Okay, so don't need to mention about the more than 10 million organic compounds because yeah, you can synthesize more and more. So now let's go ahead and get started with the review. And this I want to try and do this as fast as I can because this is not all anything new for you. You've done this in Gen Chem, so I just kind of need to go through it real quickly so you remember everything. If you need to do a little bit more review on that, then I suggest you go to my general chemistry webpage and find the PowerPoints there. And I have the lectures on YouTube as well, okay, for all of this. So quickly, atoms have electrons, protons, neutrons, and protons are positive, electrons are negative, neutrons are neutral. Then you also have the nucleus, right? Electrons are outside. The atomic weight is the number of protons and neutrons, and atomic number is the number of protons. Now, are we going to use all of these things? We will talk about all these things, okay? But I just want you to be aware that you can't forget any of this, okay? And then isotopes, of course, are going to be any element that has the same number of atomic number but different number of mass number, which is actually the number of neutrons that is different, okay, in there. So then we also deal with electronic configuration again, all right? And electronic configuration is how you will fill out the electrons in an atom. So remember, all the atoms, they have shells in them. So shell number 1, which is N, and then shell number 1, 2, 3, 4, so on and so forth. You can go on, and then you fill in the electrons, S, P, D, F, which are the subshells, okay, or orbitals, whichever whatever you want to call, it's fine. So you have SPDF orbitals, and then you start filling in electrons according to energy, right? So you have the lowest energy level that you fill electrons in first, and then as the energy increases, that's how you fill the electrons, okay? And so shell number 1 you fill first, shell number 2, and then after 3 things start getting a little bit dicey, well, sort of in and out because the energy changes, right? So you fill out the 4s2 first and then the 3d and so on and so forth, right? So that's electronic configuration. So we learn about the 3 principles to fill in the shells. Aufbau principle, which was the energy Pauli exclusion principle, and Hund's rule, which deal with how you fill electrons in the subshells also, okay? So that no 2 electrons are going to have exactly the same quantum numbers, okay? Those kind of things we deal with. Here is just a little table to show you, what the different subshells are. So SPDF, the energy of S is the lowest, F is the highest. The number of electrons that each of these subshells can hold. So S has 2, P has 6, D 10, and then F 14. F is probably the only one that you really haven't dealt with so much, right? We deal with SPD all the time. Then the shapes, okay, are important, and I can see I have an error right here. I'll fix that. So dumbbell should be, I think, only with 1B. Okay, and then the orientations in space, that actually tells you about the shape of the or the different types of orbitals possible in that one shape, right? So if there are dumbbell shape and there are 3 orientations, those 3 orientations are the P, X, Y, and the Z, right? So that's how it goes. D has 5 and F has 7. Each of the orientations will hold 2 electrons in it. So 3 times 2, 6, okay? That kind is how you fill these electrons out. So here is a little bit about the electron configuration diagrams, and the way I have it filled out here is, I'm completely filling it. I'm not really talking about the fact that if you have, a single electron left, then you just fill just the 1 electron, right? That's it. That's all you do. You don't fill the second one. And then if you have something like these 3, 3 subshells, sort of in the P. And if you have only 3 electrons in there, you fill each of them singly first, and then you start pairing them up, right? And the other thing is that no 2 electrons can have the same quantum number. So which means that when you start pairing up electrons, then you pair them in the opposite direction, which was the MS number, right? Plus half and minus half. So you have to pair them in opposite direction, not in the same direction, okay? That's wrong. So there are some of those things you still have to keep in mind. as you fill out these things. And again, we'll fill them in the beginning a little bit more, and later on it's kind of understood that you already know all of these things, so we don't have to talk about it anymore. But anyhow, so what here shows you is, of course, the first shell, second shell, third shell, and how you fill electrons in there. That's what's given here, okay? Okay, so now let's talk a little bit about bonding. Again, you know about bonding. You have two different kinds of bonding, covalent and ionic. And with the covalent bonding, it's the sharing of electrons. And ionic bonding is the transfer of electrons. In ionic bonding, you will have ions, which is positive and negative, right? Things like that. Okay, let me go through the PowerPoint here, right? Since I am recording on the PowerPoint, I might as well do this. So in the bonding, the main thing about bonding is that why do we have bonding, right? So the bonding is for stability, to get to an or lower energy state. And the lower energy state is obtained by generally having 8 electrons in the valence shell, or as we say, that's the octet rule. Why do we have octet rule? And that's because all the noble gases, which are the least reactive of all, these are all having 8 electrons in their valence shell. So either 2 for helium, which is also considered, I mean, just kind of, you can blanket in an octet, although it's the do-it rule, but it's still considered the octet rule in the sense that it is part of group number 8. Okay, and so that's the most stable kind of configuration for, or the number of electrons for elements. So that's where they would like to be. So whether they're sharing electrons or giving and taking electrons, the goal is to have 8 electrons in the last shell, the valence shell. All right, so that's how bonding occurs. That's why bonding occurs. All right, so covalent is sharing of electrons, ionic is transfer of electrons. Covalent bonding is generally between the non-metals, which is the right-hand side of the periodic table. Ionic is between metals and non-metals, where metals are the ones that form cations by giving electrons, and non-metals accept the electrons, okay, becoming anions. We will focus a lot more with covalent bonding, okay, and if you remember from your Gen Chem, that, you know, we deal with covalent bonding a lot more than ionic bonding, because ionic bonding is pretty straightforward, give and take and we're done, right? But in covalent bonding, there's so much more in there, okay? And in the covalent bonding, there is the sharing and how much we are sharing, and, you know, is it equal, not equal, how many electrons, all of those things, okay, that you have to consider. But the most important thing here is going to be our Lewis structures also, okay, because as we go on with all the bonding, you must know Lewis structures, you must follow the rules for drawing Lewis structures, okay? And so if there is any issues anywhere, you know, definitely let me know and I'll go over anything you want me to. Okay, so here are some examples of covalent bonds. Again, this is just a review because you've done covalent bonding before. Simplest bond is going to be that for hydrogen, where you're single, you know, you're sharing that single electron for the hydrogen valence electrons. So here, for example, hydrogen has 1 electron, hydrogen has 1 electron. Both of them will share, and once you share, you get a bond, right? And this bond, each of that line that is shown is 2 electrons, okay? There are 2 kinds of electrons. Let me just remind you, there are 2 kinds of electrons in any kind of bonding. One is the bonding electrons, the other ones are non-bonding electrons, okay? So here we have in chlorine, the bonding electrons are right here shown in the line, and the non-bonding are shown in the dots. Now you can show lines for the non-bonding also. I'm totally fine with that. I drew out the dots, but you can always show it like this, okay? It's totally fine. You can draw the lines like this. In fact, I encourage you to draw the lines. It's a lot easier than drawing the dots, because sometimes you can't count the dots, sometimes you can't see the dots, right? So it's much better to go ahead and draw the lines out, okay? This is just me showing you all the electrons in there. Okay, so the other thing here that I have covered is the fact that you can have a single bond, you can have a double bond, and then you can have a triple bond. And in single bond, you're sharing 2 electrons. In a double bond, there's a total of 4 electrons being shared between 2 atoms. And in nitrogen, for example, where you have a triple bond, you're sharing 6 electrons between two atoms. Okay, so it's not 3 bonds. Okay, so this would be 3 single bonds. So you understand the difference. Okay, I know you do. That's just making sure. Okay, so, oh, that's for hydrogen. All right, moving on. I didn't realize I had it there because I usually don't do all those kind of things, but here it is. Okay, all right. So here are some more Lewis structures, and here I've drawn everything out for you, showing you how all the bonding works. Now, all of this should be pretty straightforward, okay, for you all, because again, you've done this. So here's the electron dot structure, here's the line structure, here's the molecular formula, and these are some small molecules that you have dealt with before. So methane, ammonia, and then water. And then this one is called methanol. Okay, so this is a new one for you, methanol, but you've done the Lewis structures before. Okay, I hope you have at least. So anyway, so the first one with the electron dot structure just shows all the dots in there. And as I was saying in the previous slide, you can just draw the lines out. And really, this is the best way, okay, to draw structures. You should not have to draw the dots. Okay, dots can be, as I said, very confusing. Okay, so then here, what this little table at the bottom shows you is some generic idea of when you do the bonding is to not go wrong in the bonding, is to know that hydrogen will have one bond and then halogens will have one bond. Now, halogens can be a little tricky sometimes because halogens, if they are the center of the molecule, then they can have more bonds, okay? Because chlorine, bromine, and iodine are capable of forming multiple bonds. So you have to be careful. If you have a halogen and it is a terminal atom, then it will have one bond only, okay? And generally halogens will prefer to have only one bond. Oxygen will have 2 bonds, nitrogen 3 bonds, carbon, our favorite, 4 bonds, okay? If you have anything less or more than that, then you are going to have some kind of a charge, or maybe the structure is wrong. Okay, so be careful with that. And we will do formal charges in a minute, but otherwise note that, okay, that if you have less or more, then either you have a charge or your structure is wrong. Little bit about the exceptions to the octet rule, and the exceptions are 3, okay, and one of them is that you have an incomplete valence shell, which means that you don't have 8 electrons, okay. This usually happens in group number 3 because group number 3 has only 3 electrons in the valence shell, so the maximum it can bond with is 3 electrons. So 3 plus 3 is 6 electrons in the valence shell then at any given time. So that is less electrons, okay? And what happens when you have exceptions to the octet rule, okay? It means that sometimes the compounds are not stable, especially when you have incomplete shell, then compounds are not stable, which means that they will be more reactive, okay? So which means we have to deal with them differently, and this will come up, okay? Expanded valence shell is when you have more than 8 electrons. Now, why does this happen? This happens usually after the 3rd row, okay? That's when you start having the D subshell, because now the D electrons, you know, or I should say the D subshell can accommodate more electrons, okay? So for example, if you have phosphorus, which is in group number 5, and it has 5 electrons, it can have 5 sharing electrons with something else, so chlorine or hydrogen. So 5 plus 5, that's 10 electrons. So 10 electrons, you can have 8 electrons in the valence shell, right? Because in the valence shell, you have something like, not something like, you have sp, right? So s is 2 electrons, p is 6 electrons. So you have 8 electrons in the valence shell. But in the 3rd shell, you actually have sp and d, but you don't fill out the D, you fill out the D after you fill out the S, right? The 4S. So after 4S2, you fill out the 3D. Those 3D electrons or spaces are still available, okay, in something like sulfur and chlorine and phosphorus. So what happens is those extra 2 electrons, they will actually go into the D orbital. Are we going to encounter a lot of expanded shells? Probably not, because our life is going to be centered around carbon, and carbon can have only 4 bonds. It can have only 8 electrons, okay? But you need to know the exceptions. So when you have to draw Lewis structures at some point, you will not be shocked, okay, that, oh, I have to do this, okay? Or when you see a molecule or reagent, that has PCl5, you're not shocked by it, okay? You should be able to accept it and understand. Now, exceptions are always harder to remember because they're exceptions, right? So we like to remember trends. We like to remember things that we can just memorize, and not worry about it. But exceptions you have to pay a little attention to. So expanded shells are those, okay, where you can have more. So sulfur is also capable, and that's how chlorine, bromine, and iodine, they have more than one bond, is because they have exceptions to the octet rule, okay, and they can have more electrons than usual. Fluorine will never do that, for example, okay, fluorine, nitrogen, oxygen, these will never have any expanded shells. Okay, and then the last one is the unpaired electron. Okay, so unpaired electron generally happens for group number 5 because they have odd number of electrons. So when you have odd number of electrons, there are chances that one of those electrons will not be paired up. Okay, and so then you can have that exception. Okay, so then now that we're focusing on covalent bonds, let's talk a little bit about covalent bonds. There are two kinds, and one is nonpolar, one is polar covalent bond. What is a nonpolar bond? Nonpolar bond is when there is an equal sharing of electrons going on, okay? And a very simple example that of this would be something like hydrogen, right? Hydrogen is HH. So both of them are exactly the same atom, so which means that when you have a pair of electrons between them, they will share it equally, okay? Chlorine is the same way, all right? So when you have chlorine, is the same atom, but then when you have something like HCl, now these two are different atoms and they have a little bit different properties, so they may not share these electrons equally, okay? And that is called a polar bond. When electrons are not shared equally, those bonds will be polar. Now you can have slight polarity, a lot of polarity. Now, how do you determine that polarity? That is determined by electronegativity. What is electronegativity? It is the pull of electrons in a covalent bond. So, how do you determine electronegativity? First of all, to determine electronegativity, you need to remember the periodic table, okay? And electronegativity increases as you go to the right and decreases as you go down, right? So that's shown on the next slide, but we'll get there in a second. So electronegativity numbers are actually proper numbers, okay, that are given to you on the periodic table. So once you have those, you can subtract those numbers. If the subtraction is 5.5 or less than that, then it's going to be a nonpolar bond. If it is more than 0.5, then it's going to be a polar covalent bond, okay? Now, you can't remember all those numbers, and I don't want you to remember those numbers, but I would like you to do a few subtractions so it stays in your mind, in your memory cells somewhere, that you subtracted carbon from chlorine, you subtracted the carbon electronegativity from fluorine, and that way you will have at least done it once, and maybe it will stick somewhere in your memory, and you will know that, the bond between, let's say, carbon and fluorine is polar, and carbon and bromine is not so polar. Okay, so that kind of a thing, once you write it down once you do the subtraction once, it should stay with you for a while, okay? So here the example for HCl that I was giving is if you subtract the two numbers, you will get 0.9, and then that is a polar bond, okay? So that is how it works for polarity, okay, in there. All right, now let's talk a little bit about the direction of electronegativity. So here I've given you the definition also for electronegativity, and not to kind of memorize the numbers. I have given you the numbers so you have it for your reference, but you don't need to remember any of these numbers. Just do the subtraction once, as I said, and hopefully that will help, okay? So fluorine is the most electronegative element because on the electronegativity increases as you go to the right and decreases as you go down. Okay, so when you're increasing as you go right, then fluorine is the highest electronegative element. Then down, down, down as you go is less electronegative. Similarly, on the left side, of course, you will not even consider the metals as electronegative because they're not pulling electrons, and metals don't even have covalent bond. Okay, so forget about that. That's not happening. Okay, so we are dealing only primarily with the non-metals over here. So what kind of questions do you get? I know, the main thing for us is like, what are you going to ask me? Do I have to remember these numbers? No, what I will ask you is something like, you have a bond between carbon and oxygen, you have a carbon, bond between carbon and sulfur. Which one is more polar? And you will say carbon and oxygen because oxygen is more electronegative than sulfur. Okay. I'm not going to ask you if carbon and sulfur is a polar bond. Now, will you know it is a polar bond? It is going to be slightly polar because there is some difference in the electronegativity. Now, is it appreciable? And what does it mean to have an appreciable polarity? We'll talk about that also. All of these things, they all have meaning, right? We are kind of building up here into something else. So you may not have to know the number between carbon and sulfur, but you need to understand that, yeah, there's going to be a very slight polarity. There is a charge distribution, okay? Because the bond is not exactly the same, okay? In some cases, it can be the same, but in some cases, it's not the same. So if it is a non-polar bond, it's going to behave differently. If it is a slightly polar bond, it's going to behave differently, okay? And so carbon and oxygen, more polar, carbon and sulfur, less polar, carbon and hydrogen, not polar, okay, something like that. So generally the non-polar bonds, will behave different as we will learn, okay, in a minute. But anyhow, don't remember the numbers, just do the subtraction one time between all of these and just kind of remember that carbon with oxygen, fluorine, chlorine, nitrogen. These are the NOF, right? We know about the NOF from before. Those are the most electronegative elements. So those definitely are going to be the polar bonds. Chlorine is also a polar bond. Bromine, not so much, but it can be, but not so much. Okay. Similarly, carbon, sulfur, not so much, right? And we will not study selenium or phosphorus and all that. Okay. We will be kind of focused more over here, and the hydrogen, of course, from the left side. So what happens when you have a polar bond? When you have a polar bond, the molecule is not behaving in the same way. And so you end up having what is called dipole moment. Now, what is dipole moment? Dipole moment mu, the symbol right here, is the movement of a molecule in an electric current. Okay, so you put that molecule in an electric current, or you put that molecule on any kind of a solution that's nonpolar, and then you provide electric current and the molecule starts moving. That shows that there is some polarity, okay, in the molecule. And so the molecule is moving. All right, so there are a few things here that you have to consider. Two things, okay, primarily two things. One thing, there has to be polarity in the covalent bond, right? As I was just saying, that you have to have some sort of a charge distribution. The second thing is the molecule has to be asymmetric. If the molecule is symmetric, then we're going to have issues. It's not going to work. So dipole moment is a different thing. Polarity of a bond is a different thing. You can have polarity in a bond, but not have dipole moment. Okay, and that is something we're going to study. So you cannot translate one thing into the other. There is a possibility that if you have a polar bond, you will have a dipole moment. But for sure, if you have dipole moment, you for sure have polar bonds, okay, in there. So one other consideration you have to take into account in dipole moment is the symmetry of the molecule, okay? All right. Now, when the dipole moment or when the dipole difference or dipole moment is very large, that means you have an ionic bond in there, okay? So that's because you have positives and negatives. You have cations and anions, which are inherently polar anyway. So you are going to get dipole moment from there, but we are going to focus more on covalent bond. So this is a little bit different, all right? So you can have different kinds of dipole moments. It's going to be a small one, it can be a large one. That depends on the nature of the bond itself, okay? So here, this example that I've given you here for HCl, this is how we write the charge distribution. Cl is more electronegative, so it gets a delta negative. H is delta positive, okay, because now it has a little bit less electron density. Now this doesn't mean that you have positive and negative, right? It is delta. Delta means a small amount. So a small amount of negative and a small amount of positive. So it's just that, you know, when you're sharing your room with somebody and somebody just takes over a little bit more space, okay, in that room, that's all this is, okay, is that it's just the sharing is a little bit unequal. This arrow right here is very specific, and I will tell you right off the bat, okay, that organic chemists are very picky about our arrows, so you want to be careful, okay, what kind of arrow you draw. You can't just say, oh, I drew an arrow and she took off points, or, you know, this was wrong. No, it was wrong for a reason, okay? So you can't just draw an arrow and say it was correct. It's not. This kind of an arrow with an arrow and a crosshair, that is for dipole moment, okay? So how do you draw the arrow? You point it towards the negative charge, okay, the delta negative. That's how you show dipole moments. So here it is, some dipole moments given to you for some polar bonds, and you can see that, you know, how it is changing for different elements. So look through this so you can form a little bit of a trend in your mind as to how it should be. And sometimes, you know, things don't really work exactly how we want it to be. And that is something we have to live with, okay? Because things will not always follow a pattern. Generally they would, and that's why, like, throughout our organic chemistry, you will never hear me saying that this is always going to happen, okay? It's very rare that I'm going to say that this is always going to happen, because it doesn't always happen. There are always exceptions to the rule, and things behave differently sometimes under different conditions, okay? You also yourself, as a human nature, we don't always behave the same way, okay, all the time, because, you know, things change. Okay, so here let's talk about polarity and a question about dipole moment. So you will see this in all PowerPoints. I have some problems for you, so you don't think like we haven't covered any of this. There are other videos too, okay, but there are some here as well. Okay, so determine the direction of polarity in the following molecules and ions and draw the crosshair arrow to indicate the dipole moment. So I indicated here the crosshair arrow, but I'm not going to be writing that all the time, okay, in our assessments. So here are the molecules. So the first thing you have to do, okay, absolutely the first thing is you have to draw the Lewis structure. If your Lewis structure is not correct, boop, everything else is going to be wrong as well, okay? How do you determine polarity and dipole moment? So first thing first, okay, yeah, there are three things you have to do. The first thing you have to do is draw the Lewis structure. Second thing you have to do is you have to make sure that you know the shape of the molecule. Third thing you have to know is you have to know the polarity of the bonds. Okay, they're all written over here. So, you know, draw Lewis structure, draw the shape, and then determine the polarity of the bonds. I mean, if you just have to do these three things. But if your Lewis structure is wrong, everything is wrong. Okay, so be careful with that. Make sure you're good in your Lewis structures. So water, for example, H2O. This is the Lewis structure for water. We shouldn't have any issues drawing that out. Now, the shape of the water molecule is going to be bent, okay, because for water, the Axe formula is AX2E2, which is a tetrahedral. And tetrahedral is going to be this shape because this angle then is 109. And so if this is what it is, then there is an angle to it. And if there is an angle, then you will have dipole moment, because now you don't really have that kind of symmetry. You have symmetry in the sense that you have two hydrogens, but this is an angle. The way I think of dipole moment is always going to be something like a tug of war. Okay, so one side pulls the central atom and the other side is pulling the central atom, and who's winning kind of a thing is going on. So here, even though both of the hydrogens are exactly the same, you know, the angle is not the same. Okay, so because the angle is not 180, you will have dipole moment, okay, towards oxygen, because oxygen is the more electronegative element here. Okay, let's look at carbon dioxide. Carbon dioxide is this Lewis structure where you have the double bonds in there. Now this is a linear molecule. So when you have a linear molecule, in linear, the bond angle is 180. So now what is happening in here is that you have oxygen, which is delta negative, which is delta negative here. This bond angle is 180 degree because here the formula is AX2. And so once this is happening, then oxygen is pulling right opposite each other. Okay, so once they are opposite each other, this is a linear. Now this is what we were talking about before with the symmetry of the molecule. So this is completely symmetrical molecule. You can take this molecule, fold it upon each other. Okay, you might think that happens for water also, but it won't. It can happen for water as well, but for the angle. Okay, so anyway, so carbon dioxide, no dipole moment. Okay, so you can either write mu is equal to 0 or not even show any arrow. Okay, for that. Then CH3OH, which is methanol. So you write the Lewis structure first. So carbon here is the tetrahedral, and this is AX4. Oxygen here in the middle, this is just like water. So this oxygen here is AX2E2. X2 is coming from the two atoms, and the E2 is coming from the two lone pair of electrons. Okay, so the AX2E2, again, that's a tetrahedral geometry, but the shape is bent because there are only two atoms in there, right? Two electron pairs. So again, over here, you're going to have an angle, and oxygen is more electronegative. So yeah, you were going to have some dipole moment, okay, in this one. Then the last one is sulfate. Now sulfate I drew out specifically over here just to kind of remind you that sulfur can have 6 bonds, okay, because it can have the expanded shell. So sulfate has 4 oxygens all around, and then it has the 2 oxygens right here, which are a little bit different than these 2 oxygens because these 2 oxygens have double bonds. But the X formula is only AX4, okay, because there are only 4 groups over here, and the 4 groups are 1, 2, 3, 4. So AX4 is the geometry over here, which is a tetrahedral, which is fine, no problem. Angle is 109. But this is a symmetrical molecule because all around you have oxygen, 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 sulfur is in the middle. So if you have a symmetrical molecule, it's not moving anywhere. Okay, remember, one of the things that causes dipole moment is asymmetry in the molecule. Okay, so this is a symmetrical molecule, not moving anywhere. I hope this helps you understand a little bit about how you work out dipole moment. Okay, again, Lewis structure, shape, and then polarity of molecules. And know your Axe formulas, okay? That will really help you. We will go through Axe formulas slowly and slowly, so hopefully it will come back to you, okay, as we go on. All right, so one more thing to talk about here is formal charges. And formal charge is when you have an element that has either more electrons or less electrons, so it's not octet. When it's octet, generally it's going to have no charge, okay, on it's going to be 0 charge, but its formal charge is way more common than we think, okay? And just because a molecule doesn't have any charge doesn't mean it's not going to have formal charges, okay? Even a neutral molecule, maybe like NO2 or NO3, nitrogen trioxide, not nitrate ion. Nitrate ion has a formal charge anyway. Nitrate ion is NO3 minus, okay? But NO3, which is nitrogen trioxide, may also have a formal charge. You just don't see it until you calculate it, okay? So we have to calculate formal charges to know what is the charge on that individual atom, okay? Totalities are different. So you have a total charge, okay? But then formal charge is on the specific atom that you're dealing with, okay? That's how it goes. So my way of calculating the formal charge is just slightly different from what you will find in all the books. A lot of the books do, a little bit different formula, and I'll explain that to you in a minute, okay? So how I do mine. So this is my calculation. Formal charge, which here is the shorthand because I don't want to keep writing valence electrons. So formal charge Fc is equal to valence electrons Ve minus the bonding electrons, how many bonds there are. Okay, so this really is the number of bonds, and this is the key thing over here, okay, that I want to highlight for you. So it's the number of bonds, that's the Be, not bonding electrons per se, because the bonding electrons technically should be half the bonding electrons. Okay, so if you have 3 bonds, that's actually 6 electrons. So you take half of the 6 electrons, that will give you 3. So what I do, and if you want to change this for yourself and you just want to leave it at something else, you can rewrite the formula. But for me, this is the number of bonds, okay, not bonding electrons. So I just wrote it as Be to be simple, but it's the number of bonds, okay? And then, of course, you have the non-bonding electrons, which are the lone pair of electrons. But I don't want to say lone pair because the lone pair stands for 2 electrons, right? So when we say 1 pair, I don't want you to mistake that for 1 electron. It's supposed to be 2 electrons in that pair, okay? Language can be very confusing, all right? So you have to make sure that you don't confuse yourself, you know, when you deal with it. You're going to learn so much new terminology, okay, in addition to what you already know. So make sure that, you know, we are all speaking the same language here. Okay. So formal charge, this is the formula we will be using, okay? Fc is equal to valence. You first start with the valence electrons minus Be minus Ne, okay? So that's how we will get started. And then finally, I want to mention before we go on to calculate the formal charge is that the overall charge can be anything, okay? Can be +3, -2, whatever it is. But individual atoms, okay, will either be +1 or -1 or 0. Okay, they will not be. I will add the 0 over here, although I don't really need to because 0 is, I mean, it is a formal charge, but it's 0. I will add it though, okay, just so that you can have it for your reference. But formal charge of an atom is different, and then the overall charge is different. All right, so don't confuse, like if we have sulfate, okay, and we say, okay, sulfate is 2 minus, that 2 minus is an overall charge. It doesn't tell you where that 2 minus belongs. Where does that it belong? Does it belong on the sulfur? Does it belong on the oxygen? Where? Okay, that's what we have to calculate here. Okay, so let's move on. This table over here gives you a general idea, okay, of what the formal charges are going to be for us. Again, don't memorize the table. Let me just kind of go over it and try to explain, and hopefully you'll remember. Okay, so first of all, I want you to focus on the formal charge is equal to 0, okay, because this is the most critical one. Once you understand this, you will understand the +1 and the -1. So formal charge is equal to 0 means that something is happily bonded octet. Okay, that's what I said before also. So here are all the atoms that are supposed to be in their octet bonding state. Boron is 3, carbon is 4 bonds, whether it's double bond or single bonds or triple bond and a single bond, total of 4 bonds. Nitrogen is 3 bonds, oxygen is 2 bonds, whether it's a double or 2 single, doesn't matter. Okay, so these are what we say the octet states, okay, of all the atoms that we are going to be dealing with in most of our organic chemistry. When you have a formal charge of +1, things are a little bit different. When you say +1, plus means what? In our normal sense, what we think of is plus means it's a cation. Plus means it has given electrons. So if you give electrons, you become positive, right? So then you have an extra bond because you've given more. Formal charge of -1 means that you have accepted electrons. When you've accepted electrons, you have less bonds, okay, in there. You can think of it any other way you want to, okay? You don't have to follow my rules, okay? The rules don't change, okay? How I'm saying it will change, all right? So if you don't want to think of it that way, it's up to you. Generally, what happens with me is when I see nitrogen, and I see nitrogen with 4 bonds, I think, oh, it's bonding with more electrons, so it's going to be positive, okay? Because it is sharing more. When nitrogen has 2 bonds, it means it kept its electrons, to itself, so it's negative. That's how I think. Same thing with oxygen. Oxygen with 3 bonds means it's sharing more electrons, and so it's positive. Oxygen with only 1 bond means it's holding on to its electrons, and so it's negative. That's how I think. Okay, if you have a different way of remembering, you go for it. All right, that is nitrogen, oxygen, halogens. Okay, they all work the same way. Carbon, sadly, is a different story. I mean, that's why we have the whole organic chemistry, right? So carbon is a different story. Here you can see carbon with 3 bonds and being positive, carbon with 3 bonds being negative. So with carbon, you have to be careful. Okay, you have to look around and see if there are any electrons in there. So once you look at the electrons, then you will know whether it has a formal charge of -1 or +1. Okay, so be careful a little bit with carbon. All the other atoms, they should work out just fine. Okay. So here are some calculations for formal charges, and the first one here is ammonia and an ammonium ion. Okay, ammonium ion NH4 plus. So we know there is a plus charge somewhere, but does that plus charge belong to any of the hydrogens, or does it belong to nitrogen? That is what we have to find out. And so here is generally what I do for all my formal charge calculation. Here is my formula. So formal charge is valence minus bonding, number of bonds, minus the non-bonding electrons. Okay, so hydrogen is of course 1 valence electron minus 1 bond because it has only 1 bond, and then minus the non-bonding electrons, which has none. Okay, so that's 0. 1 minus 1, 0. Nitrogen has 5 valence electrons. Again, just look at the periodic table. Whatever group any element is in, that's the valence electrons as well. So group 5, 5 electrons, minus the number of bonds. So it has 4 bonds. Again, if your Lewis structure is wrong, everything is wrong. Okay, so really the key for having good chemistry foundation is good Lewis structures. Okay, and so minus 4 electrons, and the non-bonding electrons, there are no lone pair of electrons once you drew out the structure. So that's 0. That's the positive 1, which means that the formal charge is actually coming from nitrogen. Okay, so it's when you write the structure out, the plus should actually go on nitrogen. That's what it means. Okay, here is another one, and this one is for nitrate, which is NO3 minus. So in this case, you have 2 different kinds of oxygen. So you have a double bonded oxygen and a single bonded oxygen. Again, have the right Lewis structure, okay, because if that's not right, it's not going to work out. All right, so the formula is the same. Oxygen valence electrons are the same, but in the case of the double bond, there are 2 bonding electrons, okay, because there are 2 bonds in there. So 2 of the electrons of oxygen are bonding, where in the case of the single bond, there is only 1 bond in there. So only 1 electron is bonding. Then the lone pair of electrons here, the non-bonding electrons, okay, in the case of double bond, you have 4 electrons left over. In the case of the single bonded ones, you have 6 electrons left over. Okay, central atom is nitrogen. Nitrogen here, even if you didn't want to calculate, you can see here nitrogen has 4 bonds. So if it has 4 bonds, and if you learned anything from here, that when nitrogen has 4 bonds, it's going to have a positive 1 charge, right? Anyway, okay, so you see where I'm getting there. So I mean, you can learn all of these things as you go on, you know, and they start to kind of make sense. All right, and also, you know, you can take shortcuts then, because you don't want to do this all the time, right? You don't want to do all these calculations all the time. All right, central atom 5 minus 4 bonds minus no electrons left over plus 1. So here's the single bonded oxygen, you have 2. So which means you have a -2 charge, and then the atom, central atom for nitrogen has +1, so -2 plus 1, you add them up and you get a -1 formal charge, and that's that. And where is that -1 charge? That is overall, okay, but you know that the oxygen has the -2 and the nitrogen has the +1, okay, on it. So why do we do the formal charges? You will see later on as we do more chemistry. we need to know where the electron density is, okay, and where the positive center is. When we start writing reactions and the mechanisms, we need to understand where we have more electrons, where we have less electrons, because that is going to be our driving force, okay, for reactions. That's why we need to know this. And that's why I'm trying to tell you the shortcuts. So that way, when you are doing this, you don't have to keep doing all this formula every time. As soon as you see nitrogen with 4 bonds, you'll be like, that's going to be a +1. If you see oxygen with a single bond, it should be -1. Oxygen with the double bond, which is its natural state, it's 0. Okay. Oxygen with 3 bonds is going to be +1. All right. So you don't have to do all these calculations all the time. All right, so here are a couple examples for some more formal charges, and for sulfuric acid, H2SO4, and hydrogen carbonate. All right, so again, first of all, draw the Lewis structure, make sure it's correct. Don't forget sulfur has an expanded shell. Carbon does not. Okay, so it has those 3 oxygens around it. Sulfur has 4 oxygens. Okay, let me just take it one thing at a time. So sulfuric acid is this one, right? So you have sulfur with 2 oxygens that have double bonds, 2 oxygens here with bonding to hydrogen also. Remember that whenever you draw Lewis structure for acids, the hydrogen should be attached to the more electronegative element, which is oxygen in this case. So that's the Lewis structure. So which means we have to find out the formal charge for each of these atoms. So hydrogen, there is only one kind. Oxygen, there is 2 kinds, the 2 single bonds and the double bond, and then there is the sulfur. Okay. So valence electrons minus the bonding electrons minus the lone pair of electrons gives you the formal charge. And here you can see that all formal charges are 0. And let me just take you through the shortcut. Hydrogen is supposed to have 1 bond, so it is happy, 0 formal charge. Oxygen is supposed to have 2 bonds, and that's what it has. Oxygen here is supposed to have 2 bonds, and that's what it has. Sulfur can have up to 6 bonds, and that's what it has. Okay, so everything is perfectly happy. This is not the octet though. Sulfur is not the octet. So it might be worth it to do this calculation for sulfur just to make sure that you have a 0 formal charge. But otherwise, that's an expanded shell, right? So that is the only one that is kind of like iffy, and you want to check that. All the others are okay. All right, now the same thing here. If you were to do a shortcut for this one also, is carbon with 4 bonds is happy carbon. Oxygen with 2 bonds is a happy oxygen. Here also oxygen has 2 bonds, and I can see that I have an extra, no I don't, yeah I have an extra bond here. I have to fix that. Okay, so this should be a single bond and not a double bond, because no, this one is fine. This one is fine. This is the one that has, but it has an extra lone pair of electrons. So one of them should be going away. Yeah, it takes a little while to figure this out. Not a little while, but yeah, this is an extra one here. So you should have only 2 lone pairs of electrons. But anyway, once that is set, so now you have the right number of electrons in there. See if you don't have the right Lewis structure. Oh Lord. Okay. So then oxygen here with the 2 bonds is going to be fine. Oxygen here with the 1 bond should have a charge of -1. So here oxygen with the 1 bond should have a charge of -1, and it's important to write minus or plus. Okay, don't ignore that. Carbon is 0, oxygen with the double bond is 0, oxygen with the 2 bonds, single bonds, there is also 0, and then hydrogen should also be 0 because there is only 1 bond in the hydrogen. So there is 1 formal charge, okay, right here for the oxygen, which is coming from this one right here. Okay, everything else looks fine. So sorry about that, I will fix that. Okay, so that's it. Okay, as far as the formal charges are concerned, keep it simple. And that's it for this PowerPoint. Okay, and this small little chapter on formal charges, polarity, bonding, and all that kind of good stuff. Okay, so here is your keyword, and this is what we learned. The idea of giving you keywords is not just so that you know what we talked about, but also for you to write yourself little notes to see, if you understand these things. So go ahead and explain these things to yourself and see if you understand them.